Welcome back, everybody. Apologies for my delayed absence, but it was not without good cause. You see, I was finishing up my latest course, Natural Language Processing from First Principles, a beginner-friendly introduction to the core concepts of natural language processing. In that course, as in all my courses, we go through a paper, and in this case, it's the paper Distributed Representations of Words and Phrases and Their Compositionality, which is a sort of foundational paper in the field of natural language processing. Now, being a beginner course, we don't start out with a paper, we start out with a rather lengthy introduction, and in fact, we cover all of the concepts presented in the paper in a lecture format and do all of the code, and then go over the paper to see how the contents of the paper map up to the decisions I made in designing the software. A sort of backward approach if you're familiar with my deep reinforcement learning courses, which are expert level, to be fair, so I didn't want to throw in new students to the deep end straight away. But that course is live, and to kind of give you an idea on the topics we cover in there, I want to go over this paper, do a brief analysis to show you some of the power of word embeddings, and despite being such a simple algorithm, how effective it really is in learning quite a bit about human language. So right here in the abstract, they set the stage. They try to capture our attention. It says the recently introduced continuous Skipgram model is efficient and pretty much the most awesome thing ever in natural language processing, at least until that point. And they have a couple different contributions to it, subsampling and negative sampling. So let's break that down a little bit. The Skipgram model has to do with the fact that we have some large body of text, and we can scan windows, say 10, 12, whatever number of words, across that text where some word will appear in the center, and then you'll have a number of words on either side of that center word. Given that center word, what is the probability of any one word in your dictionary appearing as an outside word for that particular center word? The fundamental idea here is something called distributional semantics. The idea is that we can understand words based on their context. A word is defined by the company it keeps, so to speak. So by looking for statistical correlations between words at the center of some window and the words that appear outside in the context of that word, we can gather insights into the meaning of that word. And that meaning is represented as a vector in some high-dimensional abstract parameter space. It's not a one-hot encoding where every vector in your space is orthogonal, meaning there's no overlap in the meaning. There's no collinearity between your vectors. Rather, all of these vectors have some degree of collinearity. Some may in fact be orthogonal and have none, but for the most part there will be some overlap between word vectors because there's usually some degree of relationship between one word to another. And they've come up with a couple different ways of improving the speed with which those vectors are learned, one of which being subsampling, where you have words that appear alongside pretty much every other word, words such as the, about, and, by, or stuff like that, and the idea of negative sampling. The idea of negative sampling is that we're going to do a logistic regression where you have the true outside word and then some randomly sampled word from your dictionary that isn't that true outside word, and so you have your true distribution and a fake distribution, and you're trying to teach the model to differentiate between that bimodal distribution. Another thing they address is the fact that, in general, word vectors aren't capable of learning idiomatic phrases like Air Canada, Toronto Maple Leafs are a couple examples they give, Boston Globe. These are proper nouns where each noun by itself, each word by itself doesn't have any real relationship to the other. Boston Globe, what does that mean? You can't figure out its meaning in the context of Boston plus Globe. What they do is they treat it as a single word vector and try to proceed from there, by treating it as a single token, and actually achieve a fair amount of success in so doing. So moving down to the introduction, the idea behind an introduction is that you want to set the stage for why your work was even necessary. It's always important to guide the reader through a story like, hey, we started here with the current state of the art of the field. There are some limitations, and we want to address those limitations for whatever reason, and this is how we address those limitations. That's kind of how the paper is structured. The introduction plays into that by giving you the state of the field prior to the development of the current work. And so they talk about distributed representations of words in a vector space. That's what we just described a moment ago. Grouping similar words to get better language processing success. Moving down, they say that the Skipgram model is relatively new, and it learns vector representation of words from large amounts of unstructured text data. The important thing here is that the data is unstructured, so this is not a sort of supervised learning where we have training labels associated with our data. So it's just a raw body of text. We could feed in this paper, for instance. In fact, you could feed in a whole 1,000 papers and probably get something out the other end that had some conception of the relationships between words in a scientific field. But the basic gist there is it's all unstructured, no training labels. You just feed in raw text and let the algorithm run, and it learns quite well. In the next paragraph, they talk about something quite interesting, is that the fact that these vectors are pretty much linear, which means that you can add and subtract vectors to get different types of meaning. So for instance, Madrid, which is the capital of Spain, if you subtract Spain, the capital, from Madrid and add in the vector France, it spits out the nearest vector being Paris, which is of course the capital of France. Now it's quite startling that you can go from unstructured text data to an algorithm that understands human geography and political relationships. That's kind of fascinating to me. With a very simple algorithm, just some simple calculations of probabilities of words appearing together, gives you a pretty deep understanding of human history and kind of the happenstance of how human conflict played out over the centuries. Down here in Figure 1, they give us an example of their model architecture, and what's kind of neat is that the Skipgram model architecture is really a neural network at its core. The difference between a traditional neural network and the Skipgram model is that there is no activation of this projection layer. This projection layer is just a single matrix where you have number of rows corresponding to the number of words in your vocabulary and number of columns corresponding to the number of elements of your abstract word vector. So if you describe each word by a vector of length 10 and you have 10,000 words in your vocabulary, the matrix would be 10,000 by 10 elements. And then you deal with an output layer where you handle the activation, typically a softmax activation, for each word in the vocabulary. So it'll tell you each word's probability of appearing as an outside word for your given context word. So in this paper, they present some extensions of the Skipgram model. Subsampling is the idea that we are going to replicate our data set to magnify its size, or even not necessarily replicate it. If you have a large data set, you don't have to do that, but you can go through each sentence and toss out some words based on their frequency. So more frequent words are more likely to get tossed out, because how many times do you need to correlate the word the to every other word? Not very many, right? Whereas by contrast, words like, in the course we do the IMDb database, words like Jean-Claude Van Damme, 1980s and 90s action star, didn't appear in a whole lot of movies, and it's going to be a very rare proper noun in your reviews. And so you want to keep that as many times as you can, because you want to have as much data as possible to learn about the meaning of Jean-Claude Van Damme. So they use subsampling based on a word's frequency, as well as a variation of something called noise contrastive estimation. That's just where I described earlier the idea that you're going to have a bimodal distribution between the outside word in a context and every other word that isn't an outside word. You want the model to learn the difference between those two. And then they go on to elaborate a little bit more about the inability of word vectors to deal with idiomatic word phrases like Boston Globe, which is what they dealt with. And then finally, they elaborate a little bit more on the idea of vector addition. Adding Russia and river gives you something close to the Volga River, and Germany plus capital gives you something close to Berlin, which is, again, a pretty cool result for something so simple. So scrolling on down, they talk about the Skipgram model. It's this double sum over all the words in your corpus. That's the T equals 1 to capital T outer sum, and then you have the minus C to J to C. That's just your word window. So C would be something like 5 words, 10 words, where J not equal to 0, meaning you're going to omit the true center word in your distribution, in your window, excuse me. And then you have the log of the probability of getting your outside word given your center word. And that probability distribution is just going to be given by the softmax function here in the most basic implementation. Now, this is very costly due to the fact that the denominator here has a sum over all of the words in your vocabulary. So it's very costly to compute if you have a vocabulary of even a few tens of thousands of words, let alone a vocabulary of 790,000, which is what they deal with later on in the paper. So then they come up with, or they didn't come up with, but they implement something called the hierarchical softmax, where you represent your words as kind of like a binary tree, where you have some root center word, and then you have all your other words that appear as leaves, and then the different paths represent the probabilities of getting each of those leaf nodes. And then you can take a random walk down that binary tree to get the true probability by just multiplying the probabilities together as you go along. It gives you a pretty significant speed up in execution time. We don't implement this in the course because I figured binary trees and stuff like that would probably be a little bit too abstract for beginners, and ultimately we discover that this hierarchical softmax, while being an improvement on the full softmax, is not as effective in general as the negative sampling. So I kind of toss that aside because it's just not as effective and a little bit harder for beginners to learn. Scrolling on down, they have this negative sampling concept. So it's a variation of noise contrastive estimation, where you have a noise distribution and a true distribution. You want to train the algorithm to identify between the two distributions. You can see that it has a form of a logistic regression here. We have a log of a sigmoid function. And that's the basic idea is, as I've said a couple times before, you have your true outside word, and then you have some distribution of not true outside words, where you select those at random from your dictionary, and then make sure they don't match up to your true outside word, and then update those. And so you can see right away that this only has a sum from I equals 1 to little k, where k is something like 5 to 20, whereas up here we have this sum from W equals 1 to capital W, which is all of the words in our dictionary. And so right away we're getting a few orders of magnitude improvement, potentially even more, 4 or 5 orders of magnitude, depending on how many words in your vocabulary and how many words you choose for this not true outside word distribution. Down here in figure 2, they give these country and capital vectors projection by principal component analysis. The idea here is you're taking some subset of your space and analyzing the relationships between words in that projection of your true underlying space, and you get some consistent lines here showing the relationships between countries and capitals, and that's pretty cool. In the course we do it for other words related to reviews, things like action, boring, exciting, fun, original, scary, stuff like that, because those are going to be more suited to reviews of movies rather than countries and capitals. Another thing to note is in the caption here, they say 1,000 dimensional skipgram vectors. So we don't do anything that extensive in the course because I'm assuming people are using their desktop or most likely their laptop. And so we just confine it to 25 elements just to get the idea and to get a little bit of an idea of what's going on. And you do indeed get some interesting relationships between words using this sort of projection method. So it is successful, but we don't have the mountains of data or the time or resources to calculate these sorts of in-depth word vectors. Next thing of note is that in this final paragraph here, it says both NCE, noise contrastive estimation, and neg, the negative sampling, have the noise distribution Pn of W as a free parameter. So they did some basic studies and found that raising the frequency to the 3/4 power actually does the best. And that's kind of interesting. If you write up a sample test script with just a simple 4 or 5 word vocabulary and some basic sentences, what you'll see is that it has a property that it takes the words that appear the most frequently and reduces their probability. So if its frequency is 0.58, for instance, if 58% of your words are that word, and then you take that to the 3/4 power, you get something like 50%, whereas you have words that are like 5%, it might raise them up to 12%. So it kind of levels a playing field by lopping off the legs of the tallest person and giving a couple inches lifts to the shortest words, so to speak. So that's a pretty ingenious distribution, because it really solves the issue of words that are totally useless, filler words like the and about don't dominate your distribution, right? So you find ways to make more rare words on more equal footing with the most common words. Then they talk about subsampling of frequent words, which is kind of along the same lines. It's a similar principle here, where you reject words in your corpus based on their frequency. So this t in the numerator is some threshold, is 10 to the minus 5. And this f here, as far as I can tell, is the number of times a word appears divided by total number of words in your corpus. To get the units to work out right, that's what it has to be. And so it's 1 minus the square root of something. So it's a probability that of rejecting a word based on its frequency. For our particular project in the course, this numerator comes out to about 2.25. And so anything that appears more often than that has a high probability of or low probability of being rejected. So we have to take the max of 0 and the 1 minus square root, because that square root could be greater than 1. There's no reason it couldn't be, right? So you have to take the max of 0 and that particular square root. Then they come down here and talk about some results using a skipgram with 300 dimensional models. Again, much larger than anything we do in the course, but it gives you some idea of what sort of accuracy you're going to get. So negative sampling with 5 negative outside words gives you an accuracy of 59% with a training time of 38 minutes. Bumping that up to 15 doesn't triple your training time. It only increases it by a factor of 2.5 or so, up to 97, but gives you a couple extra points in accuracy. And they have the Hierarchical Softmax. Takes only 41 minutes to train, but only a 47% accuracy in the total tasks. And noise contrastive estimation they also do as a sort of comparison. It does 53%, kind of in between. One thing to note here is you have syntactic and semantic relationships. So syntactic is like the difference between quick and quickly. So when you conjugate words, that's a syntactic difference between the words. And then semantic has to do with like countries and their capitals. So those are the two different tasks they tested it on. And universally, you can see that the syntactic results are a little bit more favorable than the semantic. As you might expect, it's much easier to understand adding an ly to the end of a word than it is the concept of countries and capitals. Then they go on to talk about their empirical results. We've kind of started to cover this, talking about cosine distances. That's one task they did, as well as the syntactic analogies, quick to quickly or slow to slowly. They say they have an internal Google data set of 1 billion words. We don't have that. We use the IMDb database and a vocabulary of 692,000 words. That's a whole lot of words. Anything that occurred less than 5 times got kicked out. That makes sense. You probably wouldn't learn anything substantial about such words anyway. And then they deal with a potential criticism. This is kind of one of the most interesting points of the paper. So peer review is an interesting process. So for AI, it's a little bit different because a lot of these are published, quote unquote, published in like conferences. I think this came from NIPS 2013 or something like that. So they don't submit to journals in general, like Science or Nature or Physical Review Letters or Physical Review A, B, or whatever. Like I did in a PhD in physics, I had to submit to, Journal of Applied Physics Letters, and from there the paper would be sent out to 3 different reviewers who were probably people that were competing with you. And so that kind of drives who you cite, right? Because everybody in the field has a vested interest in being cited as many times as possible. So you want to kind of guess who your reviewers are going to be, because let's face it, every field of science is pretty much a small community, particularly in physics. So you kind of know, okay, we're going to get probably, out of these 10 people, we're probably going to get a handful of them. So let's cite these 10 people in some form or fashion. So that way we cover our bases. We pay respect to our competitors. So they hopefully don't have a reason right off the bat to try to take you down in the review process and shoot as many holes into your argument as possible. In AI, it's a little bit different because they don't submit to papers. They put it up on the archive, and so it gets broadly viewed by the community and doesn't have that particular aspect, which is nice. There isn't as much infighting there, but you can kind of see the result of thinking along those lines here, and it says, it can be argued that the linearity of the Skipgram model makes its vectors more suitable for such linear analogical reasoning, meaning the differences between countries and capitals, for instance. But the results of Mikhailov and others show that the vectors learned by the standard sigmoidal recurrent neural networks, which have a very high degree of are nonlinear. I don't know how you would quantify very high degree, but which are nonlinear, improve on this task significantly as the amount of training data increases. So it shows that nonlinear models also have a preference for linear structure of word representation. So it's not just the fact that you're using linear representations that allows you to take linear operations. Even if you use nonlinear operations, and you can still get linear relationships for your word vectors. So that's kind of interesting, and that's them. That's the authors here trying to head off any particular complaints about their methodology. Next, they talk about learning phrases, which is what we talked about with respect to idiomatic phrases like Toronto Maple Leafs, New York Times. The idea here is that they're going to use some algorithm to figure out which words to use based on how often words appear together, and they toss out certain stuff, and then the results there is that they get some decent results with 300 element vectors using the negative sampling as in addition to the subsampling. So you compare these two rightmost columns here. So on the bottom you have the hierarchical softmax with no subsampling. You only get 19% accuracy, whereas with some subsampling you get 47% accuracy. What's interesting is that the negative sampling is not as good as the hierarchical softmax in the case of learning phrases. So that's pretty interesting. The hierarchical softmax seems to benefit from learning phrases, so that's pretty interesting. And they were trained on a billion words from the news data set. Again, not something we really wanted to mess with in the course. And if you take a look at the examples of stuff that they learn, you can see that you get some pretty interesting results. So chess master, you got chess grandmaster and Gary Kasparov. That's pretty interesting. In the course, I kind of argued chess master to chess grandmaster isn't the best because there's a pretty big gulf between, say, an international master and a chess grandmaster. Whereas if you're thinking about chess master, who's one of the quintessential masters? You might say Magnus Carlsen if you're the modern generation. You might say Bobby Fischer if you're kind of old school. Or if you're my age, you might say Gary Kasparov. So all three of these would be probably the top three players in chess of all time, and with some arguable other players in there as well. You know, there's a handful of other players. The magician from Riga, Tal, you could argue, is one of the other great chess players of all time. So it gives some interesting results using these word vectors. Then they talk a little bit about what they do. They've got hierarchical softmax dimensionality 1000 and entire sentences context, 72% accuracy, and then they get 66% accuracy when they go from 33 billion words down to 6 billion. So you do need big data for this. So it's very powerful and startling in its capabilities, but it does require a whole big mountain of data. Then they talk about additive compositionality. That just has to do with the relationships between words like Volga River and Russia and river. When you take vector addition and sums, you get words that make sense in context. Then they do the comparisons down here to other stuff that was already available. What they did was they downloaded word vectors from these people's repositories and ran their own subset of tests. And you can see the phrase skipgram on the bottom with a dimensionality of 1000 ran for 1 day. So that's a fair amount of time, but if you scroll up, you see 100 dimensions runs for 7 days. This Turing algorithm, 200 dimensions ran for weeks, and then the one on the top with 50 dimensions ran for 2 months. And then you compare the results on the compositionality. So for instance, if you look at graffiti, that's an easy one to understand. The top one gives a result of cheesecake, gossip, and dioramas. Total nonsense, right? It totally failed the task, sufficient to say. The next model has gunfire, emotion, and impunity. Now that's kind of interesting. At first I dismissed this, but reading it, gunfire and graffiti might go together. You could have taggers waging war against each other. I haven't really heard of such a thing, but I suppose it's possible. Emotion, yeah, it may go along with graffiti, maybe. And impunity, yeah, maybe you tag stuff with impunity. Maybe the police have better stuff to do than hunt down taggers. I don't know. And then anesthetics, monkeys, and Jews. I don't know what any of those have to do with graffiti. That's pretty interesting. Then you have the skipgram, the skipgram phrase results, spray paint, graffiti, and taggers. Now this is clearly the best result of all. You could argue that spitting out graffiti again is kind of cheating, but taggers is certainly a related word. You know, taggers are the ones that go around spraying graffiti, and you use spray paint to do graffiti in general. So comes up with correct results here, so that's pretty interesting and clearly better than pretty much every other algorithm. Then in the conclusion, they just wrap everything up. You know, they have the fastest training model, vector addition, negative sampling, subsampling, and they're awesome. And all of it applies to the continuous bag of words model as well, where you're given the context words and want to predict the center word. Okay, that was it for the paper in a nutshell and about a 20-some-odd minute overview. The course is 3 hours long, where we go through all the background material with respect to the calculus. I show you all the derivations of the gradients. I show you stochastic descent, gradient descent, as well as gradients for the negative sampling, as well as some tricks they did in the paper to make this execute much faster. I go through all of that in depth in the course. If you're interested in that, go ahead, check out the link down below. It's on sale for now, $9.99. If you've been paying attention to how I price my stuff, once the initial few weeks or so are over, I'll raise the price permanently. I don't believe in selling my courses for the cheapest possible price. It's just not who I am. So if you are a value hunter, by all means, pick it up now, because in a few weeks it'll go up, not by a huge amount. It's not going to double. It'll just be a few bucks, but you know, whatever. Just so you know. And if you're not in the market for a course, make sure to hit that subscribe button, hit the like, drop a comment down below, and I'll see you in the next video.